So real quick, can you ask me, is it have directly related to this?
Yeah. So how do you, I know there's reason before, but I can't remember. Why do you not do x minus 2/3 instead of?
You could.
X minus 2/3?
You could, I could say x minus 2/3, but since I'm setting it equal to 0, why not go back and multiply through it where you don't have to deal with fractions?
Okay.
So good question. So right here, if I did write all this, would you agree that those would have been my factors?
Yes.
And if I start multiplying, you can see when you FOIL this out, you get 3x squared plus 3x minus 2x minus 2. And when you FOIL that out, you get 5x squared plus 35 minus 1 is 34x minus 7. And as I start FOILing this out, can you see that as it wouldn't be FOIL, it would be distributed property, but as I'm multiplying, can you see that the lead term is going to be 15x squared? I'm sorry, 15x to the fourth, sorry. Can you see that it would be 15x to the fourth? And can you see that I'm going to get a whole bunch of other terms too, right? But can you see that the very last term, the constant, is going to be positive 14? Now the stuff in the middle, I actually did the math on it, ends up being 107x cubed plus 3x squared minus 75x plus 14. So that's what I end up with, but it would be no easy process. And you actually had to do this in your homework last night where I give you roots and you multiply them out. Now, here's what I want you to see. You're not going to have this. All you're going to have is a polynomial, and it's going to ask you to solve. Okay? But I want you to notice that this 15 right here, what did it come from?
4 different x terms.
Yes, but it came from the 3x squared times the 5x squared. And what did the 3x squared come from? The 3x and the x, and that 5x and the x. And where did the 3 come from? And where did that 1 come from? And where did that 5 come from? And where did that 1 come from? And then if you go and you look through the constant, where did that 14 come from? And where did that come from? And that? And where did that come from? And that? And that? And that. Now the signs changed, right? So with that in mind, here's the problem. I still can't look at this and tell exactly what the roots are. But I do know this. If it's possible, my denominators in my roots are going to come from the factors of 15. And if it's possibly going to be a root, my numerators are come from the factors of 14. Now the problem is I don't know exactly in what combination they're going to be. I have no idea. But I can limit, of all the infinite numbers in the universe, I can narrow it down to those combinations. So what I'm going to do to find what we call the possible rational roots, are going to be the factors of that, which are 1, 2, 7, and 14, over, because those could be in the numerator, over the factors of this, 1, 3, 5, and 15.
Well, they always have the same amount of factors.
No. I mean, if it's a 2, 1 and 2, right? If that number's 2, if that number's 24, brace yourself, right? 1, 2, 3, 4, 6, 12, 8. You have 24. There could be zillions. But I've got to write every possible combination of them. And then on top of that, plus or minus. So the possible, what could possibly work as a root is going to be the factors of that, plus or minus 1, plus or minus 2, plus or minus 7, plus or minus 14, over a 1. And I don't really have to put them over 1 because they're already understood to be over 1, right? And then the factors of those, plus or minus 1, 2, 7, 14 over 3. So a third, 2/3, 7/3, 14/3. Plus or minus 1, plus or minus 2, plus or minus 7, plus or minus 14 over 5. So all of those fractions. And then finally, plus or minus 1, plus or minus 2, plus or minus 7, plus or minus 14 over 15. So you have narrowed all the numbers in the universe, infinity, down to a simple 32.
Yeah.
And in that 32, you can see all of our roots. There's the 2/3. There's the -1. There's the 1/5. And there's the -7. Now, is there any insight into which ones you ought to start guessing first? In real life, no. But in my class, here's my suggestion for you, since I'm the one who makes up the problems. First of all, I'm never going to give you a problem where there are this many guesses. I'm just not. Okay, you might have 8 or 12, but never on a million years you're going to have 32 roots to choose from. You'd be here all day. Okay? So here's my advice. Start here. Like if you write them out this way, now if you don't write them out this way and you have them all over the place, then that's on you. But if you write them out like all of those over 1, all of them over 3, all of them over 5, start here and then just kind of start working your way through the problems like this. Like check. I'll explain this in a second. You're going to check to see if 1 and 2 go in, one at a time. If they do, great. You'll have found one root and you'll have shrunk this down. Then you're going to go to positive and -2. You're going to try positive 2 and -2. See if they work. If they work, great. You'll shrunk it down to x squared and you'll be on your way. But if not, then you're going to come down here and check plus or minus 1/3. And if that doesn't work, you're going to come back here and try plus or minus 7. And you're going to slowly go through this list until you find enough to shrink them down. And we're gonna do a lot of these. You'll see. I'm just trying to give you the vision.
Are you plugging in the X to 4?
No, I'm doing synthetic division using that
okay.
factor theorem. I'll be checking these with synthetic division to see if they get a 0 remainder. Because unlike yesterday where I went, hey, try 3, it's a root. You knew that was going to give you 0. These are just possible. Now, if I would have made this problem up, more than likely, none of the possible rational roots would work. Why? Because it probably doesn't cross at rational numbers. If I just randomly make up a problem, it's highly likely that the solutions are irrational, imaginary, who knows what. But on the problems I give you, at least enough to shrink it down will work.
Was that a no?
Hey, that's some packages.
Oh, bucks.
Yes. The bottom one is the
Actually, it's for you.
Oh, really?
Yeah, these. Well, I might have to go through them, but they're.
This is for the library.
Oh, it's you. Thank you.
I-
All right, so again, the process is we got to start checking these things and see which ones work. But I'm not going to give you a problem. And again, you're not going to have all this. You're not going to be able to go, well, what do you mean? I see what works. You're not going to have that. All you're going to have is this. So you're going to put the factors of that over the factors of this in every possible combination. And then one at a time, start checking. You all with me?
Yeah.
Now, on your homework tonight, you look at your assignment sheet. It says do numbers to make sure, because if you don't pay attention to this, every year somebody, well, I'll just say, on the homework, you'll see it'll go page 384, oral exercises. We never do the orals. But there are a list of oral exercises, and it says, and the question is to write out the possible rational roots. But on my thing, it says don't solve. Every year somebody rolls in here on a Monday. Man, I spent 2 hours trying to solve these things. Nothing worked. And I was like, that's unfortunate. Did you read what it said next to the problems? Oh. The problems that are in the textbook, a lot of them, they don't solve. They're literally just trying to give you practice writing out the possible rational roots. Okay? The definition of possible rational roots doesn't mean this. It doesn't mean write them down and check them and see which ones are actually possible. Don't do that. It means just write them down and call it a day. Are you with me? Like, don't go in there and go, well, wait a minute, there's only 4 roots, so a lot of those are impossible. That's not what the definition means. Possible rational roots, write this down, walk away. Now, if it says solve, on other problems, like this little worksheet that I have in the book, not in the textbook, but the book, that has some problems I want you to solve. So solve those and write those down first. And I'm going to show you 3 or 4 or 5 examples, whatever. You'll be fine with this in a second. Are you with me? Okay, so that's the idea. This is how you get your logical guesses. Now, if you're thinking to yourself, well, what if the answers are irrational? They're not in there. You're right. What if the answers are imaginary? They're not in there. You're right. And if they're not in there, you're not going to find them through synthetic division unless you are the luckiest human on the planet. You're like, yeah, it's looking like a 2 minus root 5 to me. You're not going to guess those. Now, you might, but you're not. Okay? So this can only give you the rational ones, which means if I'm creating problems for you, I have to build them off at least, and I create these backwards, kind of like I did here. I'll have to create them where at least two of them are rational if it's x to the 4th. Or maybe 3 of them are rational if it's x to the 5th. And I don't give you anything bigger than x to the 5th. All right? So hopefully that helps. But again, tonight on the book work, I'm only asking you to do that part. Okay?
So if you have a rational root and you synthetically divide it into the thing,
Then you're going to get a zero remainder.
how would you end up eventually getting an imaginary or an irrational root?
Because if it's x to the 4th, which this one is, now granted, we already know, you'll see it on the first example, but we already know these are all rational, right? They're already in it. But like if I had done that, the first time you divide it in there, it shrinks down to an x cubed. And the second time you divide it in there, it shrinks to an x squared. But remember, irrational roots come in conjugate pairs. So the coefficients and constants will still look real, but you'll look at it and you go, well, that doesn't factor. And you'll plug it in the quadratic formula, and it'll spit them out. So the last 2 you will be able to find, but through the quadratic formula. Are you seeing that? Yep.
I did this one and I got +1 twice. You just write it twice.
Which one?
Never mind. I did one on.
I'm not talking about homework.
Okay.
Okay.
So this is homework?
I don't know what you're doing. What are you doing?
Review problems?
Yeah, well, whatever. That's stay with me.
Okay.
Okay, so let's look at the first example of this. Now, this particular one will be the only one I think I do today where all the roots end up being rational. Oh, I also wanted to mention this. I see people every year, they find the first one, great, shrinks it down. Then they find the second one, great. But then they keep checking the other ones. They keep trying to check the other ones in that trinomial. Guys, I'm telling you, that might help. That would work here. And you'd shrink it down to a 2-term polynomial, which is linear. You could set that equals 0, be done. But it's not going to happen on your test. I'm telling you, I make these problems up. If I make them up 9 times out of 10, if not more, the last 2 are always irrational or imaginary on purpose so that I force you to use your quadratic formula. But that will not happen on this first one, so check it out. So all you would have given to you here is solve. All right, so you got 2x to the 4th minus 7x cubed minus 26x squared minus 23x minus 6 equals 0, and you're trying to solve. Man, I certainly can't eyeball this and tell what it factors into, but I can see this. If there are roots that will work, the numerators will come from the factors of 6, and the denominators will come from the factors of 2. So I'm going to write the factors of 6 are plus or minus 1, 2, 3, and 6. The factors of over the factors of 2. So the first one's already over 1. And then I'm going to go 1, 2, 3, and 6, and put all of those over 2. Now I want you to notice something that happens here that didn't happen on the one we just did. And what is that? A couple of them reduce, don't they? Guess what? If it reduces, you already have it. So plus or minus 2 over 2, that's plus or minus 1. I already got it. Plus or minus 6 over 2 is plus or minus 3. I already got it. So don't even bother writing if you don't want to. And you'll see that what I have left Always seems to look like a polar bear. I don't know why, like, whatever. Okay, that's not true either, but whatever. So this is what I call the possible rational roots. Now again, I can't emphasize enough on a test. If I ask you for these, write them. But don't go through there and go, well, Mr. Hurry, I checked Descartes' rule and there's no positives, so I didn't list the positives. I don't want you to do that. Or, Mr. Hurry, I went through and checked all 12 of those and they didn't work. And since they didn't work, I said that the possible rational roots, there were none. I don't want you to do that. The definition of possible rational roots is, in the absence of any other information, what could you possibly begin checking with? So write those out and don't mess with them, okay? Now, who wants to start? One, that was my advice, right? Just start coming in here, tackling plus or minus 1, plus or minus 2, maybe plus or minus half, see what happens. So positive 1. Let's see if I get a zero remainder. 2, negative 7, negative 26, negative 23, negative 6. My factor theorem says if I get a 0 at the end, I know it's a root. So set that division. 2, negative 5, negative 31, negative 31, negative 54, not 6. So what does this mean?
Not a root.
1 does not work. And this line that I just ended with gave me nothing good. You don't have to draw a line through it because I might have made a careless error. And if I go through all my roots and I don't find it, I'm going to probably start going back and looking at my work and going, what did I do wrong? I missed something. All right, what about, let's try negative 1. Not in this, but in the original problem. I got to keep using the original until I shrink it down. Right? All right, here's negative 1. 2, negative 2, negative 9. 9, 17, negative 17. Nope, that's a negative 17. See how easy it is to make a careless error? So positive 17, negative 6, positive 6, 0. Sweet. I got my first root, and notice I've shrunk it down to a cubic. Right? Now, don't go back to the original. My goal is not to just define roots, but also to shrink it down. So let's work from here on out. Since this was equal to 0, I can use this. So what do you want to check now?
2.
Positive 2? So 2, 4, negative 5, negative 10. This is going south. Negative 52. As soon as you see that there's no way it's going to work, okay, that didn't work. So then I'm going to go try negative 2 into the last one that worked, which is 2, negative 9, negative 17, negative 6.
It's only gonna be 4 that work, right?
Wait, you put it into
Yeah.
the numbers out of the negative 1 because it's already a root?
Yes, because look, that part is now equal to 0. So this is now, it's already had the first root factored out of it, right?
Yeah.
So I'm using it now. I can still check it in the original, but remember my goal is to check it and to shrink it. So if I check it back in the original, I won't be shrinking the x cubed any further down, will I? And I want to keep shrinking the x cubed one down. So as soon as it works, that's now the one I'm using. So 2, negative 4, negative 13, positive 26, 9, negative 18. That doesn't work. So I'm moving on to what?
1/2.
1/2. And I'm going to, 1/2 ends up working. So I'm going to try 1/2 into 2, negative 9, negative 17, negative 6, 2, 1, negative 8. Hold on. 2, 1, negative 8. Negative 4. Wait a minute.
Wait a minute.
That doesn't work.
Hold on.
Did this work? Hold on. Am I using the right one? Oh, no. 1/2 does not work. Let's try it. Let's just pretend we checked it. Well, we just checked it. It's not working. So then we go back and we check negative 1/2. Oh, by the way, I do want to show you something. When you're checking a fraction, okay, and you see that by multiplying it, it puts a fraction in this row right here, it's never going to work, whether the fraction shows up here, here, or here, anywhere. So I kind of like doing fractions because a lot of times you multiply, you get a fraction, you put it there, you're like, that's not going to work.
Done.
Because if it doesn't work, I'm just going to continue to make a worse and worse fraction as I keep multiplying it by half. But that didn't work, but let's try negative a half. 2, negative 9, negative 17, negative 6, 2, negative 1, negative 10, positive 5, negative 12, positive 6, 0. Sweet, I found my two roots. Now I had to go through a little bit of pain and suffering, right? But I'll give you a lot of room for these. And once you find your two, where do you find yourself?
Quadratic formula.
With the quadratic. And before I go into quadratic, if I can simplify it, why not, right? Divide it by 2. And every now and then I get lucky like this one, but probably not on your test. This one I just happen to be able to factor. So Merry Christmas. But you know what? I see a lot of people factor this incorrectly. How does it factor?
-6 + 1.
-6 plus 1. I see a lot of people write x minus 2, x minus 3. But x minus 2, x minus 3 would give you the right middle term, but then it would be positive 6, wouldn't it? So be careful. Make sure, that's what I'm saying. There's really no advantage of even trying to factor it on a test because quadratic formula works great. But now I've got all 4 roots. So to solve this, you would just write my roots are -1. Ooh, -1 ended up being a double root, didn't it? -1, you only have to write it once if it works twice. -1/2 and 6. I think the book will probably write GR, like double root.
Oh, man.
But that's not necessary for you.
So once we find our 2 and what we did at the beginning, then we just go to our quadratic formula and solve.
That's a safe bet every time.
Okay.
And you say 2, if it's x to the 4th, 2. If it's x cubed, you only need to find 1. If it's x to the 5th, you need to find 3.
I think that's what I wasn't understanding earlier. So it's getting like 3 answers for an x to the 4th, but there's a double root.
So if you
Wait.
kept checking and you go through all of your possible roots, would you eventually find your 4? But all you need is 2.
On this one, I would, just because it just so happened all 4 were rational. But on every other problem I do today, you're not going to see that. Okay? Yes.
How do you know that you only need 2 roots like I just don't?
Well, what happens every time one works? Look at this. It went from having 5 terms to having, as soon as this one worked, I now have 4 terms. So now I'm going to use those 4 terms. And then when it worked again, I went from 4 terms to having 3 terms. So the second I get it down to 3 terms, it's quadratic. I can use a quadratic formula. But that would be if it starts with x to the 4th.
Yeah.
I got to get it down to 3 terms, however much that takes. But you'll notice, guys, I didn't keep trying to synthetically divide into that trinomial. It actually would have gone further down, but I got to check all these roots to find it. Why not just plug in the quadratic formula at that point? But most times, nothing will work because the last 2 are not going to be rational anymore today. At least if I do the problems I think I'm doing. Okay, let me show you another situation, and I want to see if you can catch something. So here we go. This is example 2, and this is 2x to the 4th plus 15x cubed plus 29x squared. Oh, I didn't mention this yesterday. Y'all forgot to remind me. So you're going to learn about this one.
About Descartes' rule of your
So on Descartes' rule, or Descartes' rule.
Descartes, sorry.
No, it's totally fine. Just mess with me. What does Descartes' rule tell you about this? Oh man, you're going to make me do Descartes' rule on this? No.
What's Descartes' rule?
Oh, wait, is that what?
Descartes, why check the signs.
There's no
Okay,
Wait a minute, I don't have any sign changes.
There's no positive.
There's no positive roots.
Or -2 double roots.
Now hold on, if there's no positive roots, that means there'd be all negatives. Well, were you going to sit there and write out the possible roots and check all the positives when there aren't any? That's helpful. So if all of my signs are the same, then the first check of Descartes is how many times do the signs change? None. And that's how many possible positives. So of my possible rationals, now there are no positives. Well, that would have saved me the trouble, right? If that had happened here, I wouldn't have had to check that one, or that one, or that one. I would have found my roots a lot quicker, wouldn't I? But I'm not going to tell you that you have to use Descartes' rule. But I would lock it away in my head. It's worth a glance. It's worth a glance to see if all the signs are the same. Are you with me? Yes, no? So I'm not going to check the positives, but I am going to write out the possible rational roots. So what are the possible rational roots? Factors of that 2 over factors of this 2. So plus or minus 1 plus or minus 2 over 1, and plus or minus 1 plus or minus 2 over 2. But 2 over 2 is what? So those are my only possible rational roots. No, not for possible rational roots. Remember, possible rational roots, I don't overthink it. I just write it down. But in my head, I know because Descartes, right? Because of Descartes, no positives. So if the question was find possible rational roots, I'm going to say this. But when it comes to checking them, I'm not checking positives. Are y'all seeing that? Now, if you're just randomly solving the question, yeah, you're fine to write 1, 2, and a half. That's fine, because you've already noticed that. But if the question is this, I've said this, I have it recorded, I know I've said it. The question's this, and that's all I'm asking, and you leave off the positives, you're going to miss part of it. Because if that's the question, I want to see everything that's possible in the absence of any other information like that. All right, so what do you want to check first?
Negative
-1.
one.
So 2, 15, 29, 15, 2. And 2, -2, 13, -13, 16, -16, -1, 1, 3.
You're writing faster than I can think.
Yeah.
It's so impressive.
Yeah.
How many times have you done this? Or like this example?
I made this one up a couple minutes ago.
Oh,
Oh.
Okay.
wow.
So now we're going to try what next?
1.
Negative 2.
-2?
Positive 1.
I'm not going to try positive 1
Can't.
because it's not positive. I could, but it's not going to work. All right, so let's try again. And since that didn't work, I'm going to go back to the original. Here we go. 2, -4, 11, -22, 7, -14, 1, -2, 0. Ah.
Yes.
Did it.
And I've shrunk it down, right?
Yes.
So what next?
Negative
Negative a half?
Wait, do we have to check
You
it
don't
one
have
time?
Yeah, that's the only Bible.
It's the only one left other than -2 maybe again.
But we have to get your formula.
So I'm going to try negative a half because it's still 4 terms. X cubed, I don't know how to solve that. So I'm going to go, but I'm going to use what's left. Sorry? Drop the 2. Negative half of that, -1, it gives me a 10. Negative a half of that, -5 gives me a 2. Negative a half of that's -1 gives me another 0. Great, got both roots, and I got it down to a quadratic. And because that's got a 2 in every term, I can divide a 2 into that, and I'm going to bring this up, and that gives me x squared plus 5x plus 1, which I think we can all see doesn't factor, right? Do you see why you'd be wasting your time if you had a big giant list of roots to keep trying to divide into these? Because they're not going to be rational. I'm telling you that. Now, in real life, you don't know that, but still, why would you spend extra time when you know that the quadratic formula can give you your answer in very little time? I mean, look, guys, it's not like quadratic formula really takes 20 minutes, right? Negative b plus or minus that b squared minus 4 times the a times the c all over 2a. So -5 plus or minus the square root of 21 over 2, and those are your last 2 roots. So write them out. -2, negative a half, and what I just found.
If there's an I, do you have to do the thing where you like split it up?
Absolutely. Okay. Yeah, put it in a plus b after. Now, if you had not done Descartes' rule, it's not the end of the world, right? You just probably would have checked +1 and it didn't work, -1 and it didn't work. Then you would have checked +2 and it didn't work, and then -2 and it did work, and then you would have checked +1/2 and it wouldn't have worked. So you would have just done a little bit extra. But by the time you've done enough of these, it doesn't take that long to do synthetic division, right? But maybe you add a minute or 2 to this problem and a minute or 2 to another problem, and after a while you don't have that 10 minutes that you could have used to check your work. So if you're doing everything, but again, I'm not going to do the full Descartes' rule every time. I'm looking up there and going, ooh, all the same sign. No sign changes means no positives. All right, let's try example 3. And here's another situation I'm trying to get you to see. All right, so example 3. tell you what, I'm gonna do example 4, not that, just call it example 3. All right, so we've got 2x to the 5th minus 13x to the 4th plus 33x cubed minus 37x squared plus 15. Now, actually, there's 2 things going on in this one. Equals 0. Solve.
So they're all positive, no negative.
There's no constant. That's the first thing that pops in my head. How do I find possible rational roots?
Oh, wait.
By putting the factors of the constant over the factors of the lead coefficient.
So it's
It's
zero.
zero
It's zero.
over.
So it's 0. So what does that tell me if I put 0 over 2?
They're
It's
irrational.
irrational roots.
It's irrational root.
That means the only possible rational root is 0? Does 0 work?
Yeah.
Maybe.
technically.
Yeah, plug 0 in.
Plug into 0 for-
Remember, because that's the remainder theorem, right? Says if you want to plug 0 into the function, if you get 0, it's a root, and I do. But guys, couldn't I just factor an x out? Isn't that one of the ways we solve? Take out the GCF. So if you see that there's a common factor of x, I could factor that x out, and I immediately take an x out of each one of these. But more importantly,
And you see it and you find that.
I get an answer right off the bat. Great, I've got one of them, and I've shrunk it down to x to the 4th, and now what do I have?
A constant. So you can
A constant.
do the thing.
So I can work with this now on the rest. Now, what would be my possible rational roots here? Factors of
Plus minus.
15, which are what? 1, 3, 5, and 15 over what? Over 1, and then plus or minus 1, 3, 5, and 15 over 2. And sadly, nothing cancels here. So you have 16 things you got to check. But wait,
Oh,
The car.
anybody notice something about the
They rotate. It changes every time.
they alternate? Now let me see if that's helpful. What that means, if I were to do Descartes' rule, and if you recall Descartes' rule, it was a way to determine numbers of positives, negatives, and imaginaries, right? And what we normally did is we came up here and we checked the sign changes. Now I'm working on this part right here, but that would be 1, 2, 3, 4 sign changes, right? That's a lot of possible positives. Then how did I check for negatives? I basically plugged the negative in for every x, simplified, and then counted again. Now what happens if I plug a negative in there? Nothing changes. What about there? Changes. What about there? Nothing there? Nothing.
So 0.
So, 0 negatives, because there are no sign changes on the
Which
negatives.
also means there's 4 positives, right? If there's no-
Well, it could be imaginaries,
Oh,
could be
okay.
irrationals, whatever. Or definitely could be imaginaries.
have to check the negatives.
But I don't have to check the negatives. And I just cut this down from 16 to 8. And that's pretty helpful, right? Now, if I don't do Descartes, but guess what? I'm not really going to do Descartes. I'm going to look up, and when I see all the signs are positive, that means no, when all the signs are the same, that means no positive roots, right? And when I look up here and I see all of them alternating, now there's one caveat there. They have to all be alternating and every power there. 4, 3, 2, 1, 0. If I'm missing a power, then the changes wouldn't make that all the same when you went back and put the negatives in. But if I look up here and I go, wait, plus, minus, plus, minus, plus, minus, plus, all the way down, and then every power, 5, 4, 3, 2, 1, and a constant. If I see that, or in this case, 4, 3, 2, 1 constant, if I see them all there, that tells me there's no negatives. Awesome. Then when I go to check, Descartes told me no negatives. Great. What do you want to check first? One. I'm not going to keep checking all of these. Hold on. Yeah, 1 will work. So 1, I'm going into, after the x was factored out, so 2, negative 13, 33, negative 37, 15. So 2, 2, negative 11, negative 11, 22, 22, negative 15, 0. Sweet. What do you want to check next?
3.
3, and sadly 3 would not have worked. What would you like to check next?
One half. Oh, wait, 1/2.
1/2 sadly would not have worked. But at least I'm checking positives, right? Then what?
5.
Yeah, and sadly 5 would not have worked.
3 halves.
3 halves would have worked. So you still would have had to miss some stuff, right? But I'm trying to save us some time. But eventually you get down, right? Eventually you get down to 5. And I'm checking 5 again into the last thing that had a 0 remainder. All those other ones I would just be rewriting this 2 and -11, 12, -15 each and every time. 2, 10, -1, -5. -1, -5.
Yeah.
Wait, does 5?
Wait, you said 5?
No, 5 didn't work. Man.
So it was 3.
Yeah.
3 halves, yeah, sorry. 3 halves is the one that ends up working. So 2, that times that. 3, -8. That times that. -12, 10. That times that. 15, 0. And if at any point I got a fraction on that middle row, then I'm done. Or I made an error. And look what I've done.
And then you can simplify by
I've got it to a quadratic. You can certainly divide a 2 out to make your math a little more simple. And look, that is just begging to be factored, but guess what? It doesn't. I see people all the time, they go, oh, x minus 5, x plus 1. Nope. Oh, x minus 5, x minus 1. Nope. Dude, it is screaming to be factored, isn't it? That is probably the most overly factored, wrongly factored trinomial that I have.
It's just so pretty.
I know, it's just begging, factor me, factor me. It does not factor. So, but again, if you just get in the habit of quadratic formula, negative the b plus or minus b squared minus 4 times the a times the c, all of it over 2a, I get 4 plus or minus, what's 16 minus 20?
Negative 4.
-4,
So
take the
2i.
I out, so 2i, all over 2. What does that simplify to?
2 plus or minus I.
2 plus or minus I. So your roots, 1, 3 halves, 2 plus or minus I. Right?
Wait, but. Never mind.
Now, if you had not done Descartes' rule, man, remember how many we skipped?
16.
3.
Like we tried plus or minus 1, -1 you would have tried, plus or, and an extra -3, and an extra -0.5, and an extra -5. You would have tried probably an extra 3 or 4. You would have gotten really frustrated. So I'm just saying it is worth looking and going, oh, all the same signs? No positives. I mean, lots of positives, no negatives. No, all the same signs, no positives. Alternating signs, as long as all the powers are there, no negatives. That's worth it. If I don't have that, I'm not bothered. It's not going to be that helpful. It's just not. Maybe if I had 30x to the 30th, and I was going to be here all day, maybe, but it's just not worth it. All right, what about this? And this is the last little tricky one I want to show you. Okay, x to the 4th minus 7x cubed, 17x squared, minus 16x plus 4 equals 0. Oh, wait, alternating signs. What does that tell me?
No negative.
They're alternating signs. That's 4 positives. So my PR possible ratios are plus or minus 1, 2, and 4 over 1. Well, that's it. And then I don't have to check negatives because of Descartes, right? So Descartes says no negatives. Well, that's easy, right? Let's just start checking. What do you want to check first?
1.
So 1, -7.
Let's just put 1 first. Oh, wait.
You did it.
Yeah, sorry, I was probably the one. So let's check 1, and sadly, no, just missed. Not 1. All right, so we go to 2. Back into the original, since it didn't simplify. Here we go. 1, 2, -5, -10, 7, 14, -2, -4, 0.
Yay.
Sweet. So it worked, so I'm gonna go with that. And then I know based on this, 4 must work, right? If you sensed a hint of irony. Oh no.
Oh, no.
Now what does that mean?
Double root.
It means that there might be a double root, or it might mean you made a mistake. But good thing I can see everything. So maybe I go back and go, well, hold on. Did I do the math right on 1? Yeah, I did. Did I do the math right on 4? Yeah, I did. Well, maybe it's a double root. Now, I'm not going to go around checking every one that works initially. And also, I'm not going to give you one that has a double root when you have 32 possible rational roots and make you check all of them. But you'll notice I didn't really make you have that many rational roots, right? And Descartes eliminated half those. So it wasn't that hard to check everything and go, wait, let me check 2 again. Back into the last thing that worked. 1, 2, -3, -6, 1, 2, sure enough, double root. And I can take this last part and solve using the quadratic formula.
Oh, did you put 2 back into the bucket again?
Yeah, it ended up working twice. Who knew? And here we go. B plus or minus, or negative B, B squared minus 4 times A times C over 2 gives me 3 plus or minus root 5 over 2. And if you're wondering, wait a minute, I thought they were all positives. This is plus and minus. But what's root 5? 2-ish? What's 3 minus 2-ish?
1-ish.
Still positive. So even though there's a negative in that, you can still see that all of my roots, especially the possible.
Wait, do we have to write 2 twice?
No, sorry. Definitely not. So 3 plus or minus 5 over 2. If you want to know, like, why don't you write them twice? It kind of like if I said, let's just say you had a twin, right? And somebody asked your parents, hey, what are your children's birth dates? Right? I don't have to list you and your sister's birth date twice, right? I'm just listing birth dates. When somebody says solve, they're essentially saying, which x's make this true? Those x's make it true. You don't have to say the same thing twice to answer that question. All right, guys, remember the bookwork, don't try solving those or you're going to be cussing me.
Oh, I think I'm okay.
What?
I have big handwriting because I have big ideas.
On the bus?
Oh, no. Stop, the butterflies came in.
Oh, wait, that's just the.
They fluttered. If I got a 90, I think I'd still try.
Hey, not.
What time? I got a 60. Yeah, it's just like, this ranging in other fish. The thing is, like, I've quit mystery, so I've reached my peak. I know I've reached my peak.
Yeah. They're soft.
We talked about like some senior, and she was like, David, he's so smart. He doesn't care. He's over there back there. Walker.
Why did they do that?
Yeah. It was so smart. Yeah. He was like Mr. House. It looked like he didn't answer. Yes. He's like, I go to the bathroom. And she's like, oh, my God, you're already in the answer. He walks in. He's like, -179. He's like,
All right.
Yeah.
All right.
My dad wants to rent a game for next weekend and drive up to my volleyball tournament and spend that in RV.
Yeah.
He does that. Russell and Avery live with my name in their contract is spelled really spelled.
Yeah, mine is too.
Are you for real? Is yours?
I'm sorry, have a good weekend.
Thanks, man, you too.
I had to change it back because I said all Taylor, but. I don't want to say that every time. I mean, either way.